Picture this. You've just spent weeks, maybe even months, training a machine learning model. The accuracy's off the charts, your notebooks are beautifully clean, the loss curves are perfect, and when you show it to your team, everyone is just blown away. But then, what happens next? Usually, absolutely nothing. It just sits there in a Jupyter notebook. It literally never serves a single real user. And, 6 months later, someone else ends up retraining the whole thing from scratch because nobody actually remembers how the first one was built. Welcome to this explainer. Today we're going to dive deep into how tech giants actually get their models out of notebooks and into production.
Crazy, right? But that opening scenario isn't just some hypothetical I made up. It's the shocking reality for roughly 87% of machine learning models built in organizations today. They simply never make it to production. And the reason? Well, it's almost never the model itself. It's the fact that building a model in a lab and actually operating one in the wild are two completely different engineering problems.
To really put that into perspective, over at Google, the actual machine learning model code, the fun part everyone focuses on, makes up less than 5% of the production system. Literally less than 5%. The other 95% of the engineering, that all happens in the surrounding infrastructure. We're talking data pipelines, feature stores, serving infrastructure, and monitoring systems.
So here's our roadmap for this explainer. We'll kick things off by defining what MLOps actually is, then run through its 6 core stages. After that, we'll see this stuff in action at massive scale by breaking down the architectures at Netflix, Uber, and Airbnb. And finally, we'll wrap up with the massive career opportunities waiting in this space.
All right, part 1. What is MLOps? Let's start with the basics. What actually is MLOps, and why is it the glue holding production AI together? Well, it stands for Machine Learning Operations. Think about traditional software engineering for a second. You don't just write a bunch of code and email it to a buddy. It goes through version control, automated testing, and a proper deployment pipeline. MLOps brings that exact same operational rigor to machine learning. But here's the kicker. Unlike traditional software, where you're mostly just managing static code, ML systems require you to juggle code, data, models, and predictions all at the exact same time. The code might stay the same, but the real world is messy, and data is always changing. If that data drifts or a feature breaks, your ML system can fail completely silently. And that right there is exactly why MLOps is an absolute necessity.
Moving right along to section 2, the 6 stages.
To prevent those terrifying silent failures, the industry relies on a continuous 6-stage loop. This is really the heartbeat of the MLOps lifecycle. It takes you all the way from raw data to a continuously monitored live system. It kicks off with data, pulling it, cleaning it, versioning it. Next up is features, where we transform that raw data into actual signals. Third is training, where the model learns from those features. Then comes evaluation, which acts like an automated bouncer to ensure quality. Fifth is deployment, wrapping the model securely behind an API. And finally, monitoring, which is keeping a constant, watchful eye on the model to make sure it stays accurate over time.
Now, if there's one thing you take away from this, it's understanding the massive gap between stage 2 and stage 5. This gap creates what we call training serving skew, and it is hands down one of the biggest killers of ML systems. Your training environment is nice and cozy. It uses static historical batch data. But your serving environment? That's the Wild West. It deals with dynamic, real-time data and strict latency constraints. It's kind of like practicing for a marathon on a treadmill and then trying to run the actual race in a hurricane. If your features are calculated differently in those two environments, your model is going to behave completely differently in production than it did on your laptop.
So how do we fix the reproducibility problem during that training stage? Well, the industry standard right now is an open source tool called MLflow. It's actually pretty brilliant. By just wrapping your core training block inside a super simple start-run statement, the system automatically takes the wheel. Notice how the log param function quietly tracks your hyperparameters, like the 100 estimators right there, and then log model bundles up and saves the fully trained model as a versioned artifact. It means that, 6 months from now, you will know exactly what data, what parameters, and what exact code produce that specific model. It gives you absolute 100% reproducibility.
Let's move to section 3, Netflix and pipelines.
Let's zoom out and see how this actually works at planetary scale. We're going to look at Netflix, where the recommendation engine is quite literally the core distribution mechanism for over 200 million users. They pull this off using a massive 3-stage pipeline, carefully balancing the cost of really cheap early filtering with the sheer quality of an expensive final ranking. First, they do candidate generation, taking tens of thousands of titles and filtering them down to about 10,000 using super lightweight models. Next is the ranking stage, which brings in the heavy, deep neural networks to score those candidates. Finally, re-ranking applies business rules and injects diversity, so you're not just staring at a wall of 50 action movies. Managing multi-stage pipelines at that scale is no joke, so Netflix actually built their own framework called Metaflow to handle it. And the real magic here happens with just a tiny little at-step decorator. By slapping that onto a Python method, Netflix ensures that every single chunk of the pipeline is independently versioned and, more importantly, resumable. Think about it. If a massive, heavy ranking step fails halfway through a giant compute job, you definitely don't want to rerun the whole data loading process from scratch. With Metaflow, you just resume from the exact step that failed. That kind of rock-solid fault tolerance is an absolute must-have at Netflix's scale.
Section 4, Uber and Feature Stores.
All right, let's jump over to Uber and check out how their Michelangelo platform tackles feature engineering. Remember that nasty training serving SKU we were talking about earlier? Well, Uber's brilliant fix for that was centralizing all their features. Using Feast, which is a fantastic open source tool, you just define a feature view, like driver stats, for example. And here's the best part. By simply setting online equals true, the system guarantees that the exact same feature logic you used for your historical training is the exact same logic served up during real-time online inference. It computes everything once, guarantees byte-for-byte consistency between offline and online, and just totally eliminates that SKU problem.
Section 5, Airbnb and Deployment.
Now, let's talk about Airbnb. Their Big Head platform is honestly a masterclass in how to deploy models safely and completely automatically. They use Kubernetes native pipelines to handle the heavy lifting. With Kubeflow, you can actually hard code an accuracy threshold, let's say 85%, straight into the pipeline's logic. So the pipeline runs the training task, right? But that deploy task is only going to trigger if the model actually hits or beats that 85% mark. It's basically a highly strict, automated bouncer baked right into the code. No human has to sit there manually reviewing and approving the model. If it's good enough, it just goes live.
But pushing to production is really just the starting line for the final stage, which is monitoring. This is where you bring in an industry-leading tool like Evidently. You essentially create a report and plug in a data drift preset. What this does is it automatically compares your historical reference data against the live data flowing in right now, running statistical tests on every single feature. So if the real world suddenly shifts and your data starts drifting, this catches it instantly. It can even be wired to automatically trigger your pipeline to retrain the model before the accuracy ever drops for your users.
Okay, let's take a quick breather and look at the big picture. Here's a handy cheat sheet mapping out the entire MLOps tool stack we've been walking through. For tracking your experiments, you've got MLflow and weights and biases. For orchestrating the pipelines, Kubeflow, ZenML, and Metaflow are the heavy hitters. The feature store space is dominated by Feast, Tecton, and Hopsworks. When it's time for serving, BentoML, Selden, and Kserve are top tier. And for monitoring, Evidently, Arise, and Fiddler really lead the pack. Getting familiar with this specific ecosystem is just incredibly valuable.
Which brings us nicely to Section 6, Careers in MLOps.
Speaking of valuable, let's talk about what all this actually means for you personally. MLOps isn't just cool tech. It is legitimately one of the fastest growing engineering roles on the planet right now. The financial upside is huge. Over in the US, average salaries for MLOps engineers are hitting up to $220,000. And in India, top roles are ranging anywhere from 25 to 60 lakhs a year. The demand is just drastically outpacing the supply of engineers who actually know how to build these pipelines.
But to land one of those roles, you got to pass the interviews. Like this real question straight from Google and Uber. When they ask about training serving SKU, the correct answer completely relies on understanding feature stores and a concept called point-in-time correct joins. That's just a fancy way of saying you need to match your historical training data to the exact state of the world at the very millisecond an event happened. It guarantees your offline training perfectly mirrors your online inference. Here's another top interview scenario they love to throw at people. Based on what we've talked about today, your answer should definitely involve setting up statistical drift detection, like that Evidently tool we just looked at, and then tying its alerts directly to your automated CI/CD deployment pipelines. That way, your entire system triggers retraining completely seamlessly without a human ever having to intervene.
Let's bring this all together. I think this quote hits the nail on the head and summarizes the core philosophy perfectly. MLOps isn't just downloading a specific tool, and it definitely isn't a magic bullet. It is a rigorous engineering practice. It proves that scaling machine learning to millions of users isn't magic. It's just really, really great engineering.
So I want to leave you with this final thought. Out of everything we covered, Which part of this continuous MLOps lifecycle do you find the most challenging to build? Is it setting up those feature stores, automating the deployment gates, or maybe dealing with the drift monitoring? I highly encourage you to dig a little deeper, grab a few of those open source tools we mentioned, and start building your own production AI pipelines. Thanks for hanging out with me on this explainer, and keep learning.